Hello. We're going to continue our ease into proofs with some algebraic demonstrations, so to speak. Every time you solve an algebraic equation, you're in a sense running through a proof. You just don't lay it out like a proof every time, at least not usually. If you've been watching my videos, I certainly don't do it. I do most of it in my head and just wave my hands around the rest of it. But this time we're just going to have to do it step by step to show that it really is very much like a proof. We just justify each step. For instance, dividing both sides by the same number, adding the same amount to both sides. All the usual things you do to solve algebraic equations. All we have to do is list the justification for each step, and it's very much like a proof. So here we have major algebraic properties that we're going to use, and we will just, in a step-by-step way, solve equations and make use of these properties in a way that isn't exactly a proof, but it can be called a demonstration, or when you see in a book where it says show that. It's not really a hardcore proof, but it's pretty close. And that's what we're going to do. There's not a whole lot to say about this because you've already done a lot of it. And this is almost just a review, but it's just to kind of re-solidify what you already know about justifying each step in the solution of an algebraic equation. And it's a very similar method that you're going to use in the next section when we do some actual geometry type proofs. So let's just get to doing some problems here. There's not really too much else to talk about here. So let's look at these here and see what we would do. These are pretty easy. In fact, I'm sure you know exactly what to do. All we have to do is just make sure that we justify each step, unlike what you've probably seen me do up till now. Let's add 10 to each side. So plus 10 here. Oops, pardon me. So if we add 10 to each side, we get 5x equals minus 30. And why can we do that? Addition property. We justify it over here, addition property. What do we do next? How about we divide by 5? That would give us x equals minus 6. And how do we justify that? Right here. This is the one that says we can divide through by the same number on both sides. So we have the division property. And we're done. And now for the next one, what are we going to do? Well, we're going to use the addition property a couple of times, aren't we? First thing we can do is add 3x to each side. So that's plus 3x here and plus 3x over here. What does that give us? 7x plus 9 equals 16. Now, suppose we subtract 9 from each side. And remember, this was our addition property. I have to be careful to write this in because that's the whole point of this section. That's the addition property, which allowed us to write 7x plus 9 equals 16. Now we're going to add a minus 9 to each side, once again using the addition property, and get that 7x, and that'll be the addition property also. 7x. Well, that's really a bad x. Let me try that again. And it looks more like an x. And applying the addition property twice here, we get 7x equals 7. And then x equals 1. And that is when we divide through, we multiply by 1/7 over here and 1/7 over here. When I write it this way, I'm actually using the multiplication property, aren't I? And frankly, I don't understand why they even separately list addition property and subtraction property, multiplication property, division property. Come on. I think you're sophisticated enough to understand that if this is true, subtracting is just adding a negative. So if you can add c to each side, you can add a negative c to each side. If you can multiply by c, you can multiply by 1 over c. I don't like either one of those properties, to tell you the truth. I think you're better off just having two properties and then recognizing, as most of us do, and you shouldn't have any trouble by now, recognizing that subtracting c is the same as adding minus c, dividing by c. It's the same as multiplying by 1 over c. So these, I probably won't cite them very often. And as you're, if you're doing it, you can check with your teachers who will be grading your state exam. But I'm pretty sure that if you write what I did and say, this is the multiplication property, and don't even talk about the division property, I bet they'll give you full credit. I know I sure would. And do we really need to look at this one? Yeah, what the heck, we're here, let's do it. And once more, we're just going to do exactly what you already know how to do. We're just going to make sure that we itemize each individual justification for our steps. Here, obviously there's two ways we could do it. We could use this distributive property and get that 15x minus 100 equals minus 10. And then we'd probably just end up dividing by 5 anyway. So let's multiply through by 1 over 5. That's what I'm going to call it. I'm going to say we're going to multiply by 1 over 5. I don't have to worry about dividing. If we do that, that'll be 3x minus 20 equals minus 2. And that is the multiplication property. Allowed us to go from there to there. Now, I would say we add 20 to each side. So, let's see here. Plus 20 up there. And plus 20 up here. That would give us 3x equals 18. And that was the addition property, which allowed us to do that. Next, we multiply by 1/3 on each side and get that x equals 6 through the multiplication property. Okay, have fun yet? Okay, here's one here. Right here. It's exactly the same, but different. And what the heck's he talking about? What I mean is, before we were solving for x, period. We only had one variable. Now we've got two variables. That's something to pay close attention to. Don't just run around thinking you're going to solve the whole thing when you got two variables and only one equation. But you can solve it for one of them. For instance, when you solve an equation for x, you write x equals, and all the other stuff is on the other side. When you solve an equation for y, you write, put it over here, y equals, and a whole bunch of stuff over here. That's solving it for y. So, how do we do this? Well, let's see here. Our addition property says we can add minus 5x. Yeah, I know they call it subtraction up there. But I'm going to add a minus 5x over here. Say plus a minus 5x, just to make it clear I am using the addition property, not the subtraction property. Plus minus 5x. That leads to y equals 18. That's the great thing about arithmetic with variables. There's not much left to say other than 18 minus 5x is 18 minus 5x. Done. That's about all there is to it. And that's what you do whenever they say solve for y. Just keep in mind you're not going to look for an actual number. Well, unless there were any x's, of course. So this is almost exactly what we did previously. Just pay close attention when they ask you to solve for y. It usually means they're just looking for an equation and not an actual number. No big deal. Here's one involving properties of equality. And they're over right here on the right. This stuff here. It's reflexive. And these properties of equality, they're listed for the sake of being able to point to them whenever you use them. They're not intended to be a big surprise. For instance, number 1, A equals A. Can we just stop right there? Do we really need any more explanation for that one? I don't think so. I'd buy into that immediately. What about down here? If A equals B, then B equals A. Well, for an equality, that's always true. No problem there. And it makes sense, too. After all, would it make sense to say that if one thing, well, first it's down here with line segments. I mean, would it make any sense to say that AB has the same length as CD, but CD doesn't have the same length as AB? Wait a minute. That sounds like a comedy routine. It doesn't sound like mathematics. So, yeah. If A equals B, then B equals A. What about transitive? Well, that's pretty much like what we called the chain rule before, isn't it? Remember in logic, we could just put implication symbols right up here. If A implies B, and B implies C, then A implies C. And back in logic, we called it the law of syllogism. Chain rule's good. Transitive kind of points to what it really is. I mean, you're transitioning in a sense. You're saying that A equals B and B equals C, and you can just transport by dropping the two B's and go straight through B all the way to C. If that doesn't make sense to you, then just memorize the fact that it's called transitive. And this one's fairly obvious, but maybe less obvious than the other two. So now we have a question down here. Name the property of equality the statement illustrates. And here we must be talking about line segments. And who cares? Doesn't really matter. What matters is the property we're using here. And let's see, we've got xy equals AB, AB equals GH, and that implies that xy equals GH. Well, what did we do? We just kind of went straight through the AB, jumped over it, went from XY to GH here. And that was that one, wasn't it? Now in these next few, all we have to do, they give us the property to use. All we need to do is determine what does this property lead to given this equation. For instance, if we have AB equals CD, then what can we deduce from the addition property of equality? Given this, what could we fill in here that would be accurate? Well, how about AB over here and CD over here? Because the addition property says if AB equals CD, then we could add the same thing to each side, which is what EF is, the same thing on each side. So, boom, that's it. Distributive property. Well, you guys know how that works. So if we apply the distributive property to this equation, we would of course get that 5x plus 40. 5 times x here, 5 times 8 here. 5x plus 40, not very good writing, equals 2. And the transitive property. This is the one where you just kind of shoot through the middle one and go straight from there to there. So, we would have the measure of angle 1 equals the measure of angle 3. Boom. Real easy. Here we have another one of those great error analysis problems. And here we have the instructor wrote this. Yeah, it's the teacher, not the student. The teacher did this all wrong. What did he do wrong? Well, this part looks right. That's given. So given's always right because it's given. If they wrote 3 equals 2 and next to it wrote given, then you just have to accept it as true. So what's wrong here? Well, let's see. We add x to each side and get 8x. That would be the addition property of equality. The problem is we needed to add a minus x. In other words, subtract x from each side and get that 6x equals 24. Now, the next part, once you've made this mistake, there's nothing wrong with this part here. If this were true, then x would in fact equal 3. The problem here is, and I don't really like the way they implied this mistake, because the problem is an arithmetic mistake. He added here when he should have subtracted. If you write it out, minus x on each side, it becomes more obvious. And if you've watched other videos, you've seen me make exactly this mistake when I'm doing it in my head. But the mistake isn't the application of the property. So it's possible they're looking for, you should have subtracted and used the subtraction property. Well, you should have added a negative x and used the addition property, because I just don't see the point of having a subtraction property. But the error, either way, is you should have subtracted x, well, pardon me, the instructor should have subtracted x from each side. He or she didn't do it and wound up with this erroneous equation, which led to this erroneous answer. But the step from here to here, that's fine. If this were true, this part would definitely be true. But this isn't true, because obviously you just made a simple little arithmetic mistake here. This is the kind of problem you will, not exactly with 3 columns, but filling in the blanks. You'll see that on the standardized tests, rather than just having to start with a vacuum and write out the whole thing. They'll give you parts of it and have you fill in the blanks. It's usually a little bit easier. Explanation and reason. Well, I'm going to give you a little tip of what's coming up. We're going to do in upcoming section something called a 2-column proof. I've never heard of a 3-column proof. I think this is just to, again, help ease you into the idea of a proof, because reason and explanation, what's the difference between the two? Well, I think over here they're just saying, what did you actually do? Like add the same thing to both sides, or divide by the same thing on both sides, and something like that. Over here, I think what they really mean is what they would really call justification. In a proof anyway, you have to justify each step. I think that's what they mean here. Well, I know that's what they mean. So don't be confused by the fact that they're asking for apparently the same thing in each column. It's not the same thing. It's over here, it's just exactly what did we do, and over here, why did we do it? I'm not even sure what they mean by this, because it's given. So what did we do? We didn't do anything yet. I don't think. Let's see here. Well, maybe we did. For explanation here, you could just refer to the diagram, I suppose. Angle 1 equals measure of angle 1 equals the measure of angle 4. Well, they drew that in here. See, they both have the same single hash mark. And that these are both 90-degree angles. Well, they put in those little red right angles to demonstrate that that's what they are. So I guess diagram would be about the only thing you could put in here. This is all given. Now, what do we do here? Well, we replaced angle 90 degrees with EHF here, and 90 degrees with the measure of angle GHF here. We might have used the transitive property also. If we'd written this a little differently, it would be apparent that the transitive property allows us to write this also. But over here they wrote substitution property. So in here you would just write replace angles. And I don't have room to write it in, so you didn't have to replace the right angle, the 90-degree angles, with the actual angle labels and not the 90 degrees. Add measures of adjacent angles. Aha. Now what says we can do that? Well, let's take a look up here. Well, remember back a long time ago, we had our angle addition postulate, just like our segment addition postulate, which says that if you break up an angle, the sum of the angles adds up to the whole. Here's EHF, and here's the two angles we broke it up into. If we add them back together, we get the whole again. That's our segment addition, our angle addition postulate. Call it angle addition postulate. Over here we wrote the expressions equal to the angle measures. Well, this is 90 degrees, so here we could have done the same thing, as I refer to this as possibly using down here the substitution property, or pardon me, the transitive property. Well, we can do that here. Although it's kind of doubled. These two are equal. Since this is equal and this is equal, I would say we could use our transitive property to just cut out the middlemen here and write that this equals this. Why? Well, it's a combination of step 2 plus your transitive property. You could also use step 2 combined with, no, I'd stick with the transitive. Remember, transitive and substitution are so closely related, we could use both of them. But step 2 tells us that these two are equal. This is equal to that, that's equal to that, so you put them together. It sounds, when you write it, when you say it that way, it sounds more like the transitive property. And here, now we have to figure out what is the next line. Well, what's our goal here? We want to show that this angle equals this angle. I can't write as small as these guys type. But we're given that M1 equals the measure of angle 1 equals the measure of angle 4. So now we can substitute. We substitute angle in, the measure of angle 1 in for the measure of angle 4. We get the measure of angle 1 plus the measure of angle 2 equals the measure of angle 3 plus the measure of angle 1. And now we can use our subtraction property to subtract the measure of angle 1 from each side. And down here you just write subtract measure of angle 1 from each side, because they said subtraction property. I would probably write add negative measure of angle 1 to each side. That's entirely up to you. And over here, well, obviously it's the substitution property. We substituted. So I expect the answer they're looking for is substitution property. And we use that one up here too. So just write it again up here. And like I said, down here just write subtract measure of angle 1 from each side. These are the kind of tests that you, questions that you probably will see on the standardized exams. And this is exactly the kind of thing we're going to do a whole bunch more of in the next sections. But it'll be 2 columns, not 3. If I seem to be stumbling over these, it's not your imagination. I am stumbling over it because I don't know anybody who's actually used to doing it this way. You usually write the next line and then the reason for it. You can kind of see what happens, so you do it and then you write the reason. They're being kind of redundant here, but that's in order to, as I say, ease you into the idea of a proof. And it also helps to confuse people like me. Well, that's it for now. We'll see you next time when we're going to do